Hello there, and welcome to the Cosmic Sleep Science. I am so glad you are here. Maybe it has been a long day, or maybe you are the kind of person who likes to fall asleep thinking about distant planets and drifting moons instead of counting sheep. Either way, tonight's journey is for you. You don't need to do anything now but rest. Let your breath slow, your thoughts soften, and your body grow light as if gravity has loosened its grip and you've begun to float quietly through space. Because tonight, we're going to drift gently through the universe, not in a straight line, but in soft spirals from glowing nebulas and ancient starlight to whispering galaxies and cosmic voids that stretch beyond imagination. A story told not in numbers, but in celestial dances, quantum whispers, and light that has traveled for eons, from collapsing stars and warped spacetime to cosmic horizons where reality bends. Every corner of the universe holds something strange and beautiful. We'll go slowly, gently, just one sleepy fact at a time. And just before we begin, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. It helps others find their way here, too, one sleepy soul at a time. Now, let's begin. The universe is mostly empty space, a vast cosmic ocean of nothing. When you look up at the night sky filled with countless stars, it is easy to imagine that space is crowded, with celestial bodies competing for room. But the truth is far more humbling and strange. The universe is predominantly void, an incomprehensible expanse of emptiness, punctuated by tiny islands of matter, between galaxies, between stars. Even between the atoms that compose your body, there exists vast nothingness. If you could somehow remove all the empty space from every atom in every human being on Earth, the entire population of 8 billion people would fit into the volume of a sugar cube. Let that sink in for a moment. All of us compressed together would barely fill a teaspoon. Space itself is the dominant feature of existence, a silent canvas upon which matter plays out its brief performance. And this emptiness isn't truly nothing at all. It hums with quantum fluctuations, permeated by mysterious dark energy, filled with invisible possibilities waiting to unfold. The vacuum seethes with virtual particles, popping in and out of existence. The universe breathes in the space between things, expanding eternally into its own infinite void. Every atom in your body was forged inside a dying star billions of years ago. The carbon in your muscles, the calcium in your bones, the iron flowing through your blood. None of these elements existed when the universe first began. In those earliest moments after the Big Bang, only the lightest elements, hydrogen and helium, filled the cosmos. Everything else, all the heavier elements that make up planets and people, had to be created later. And the forge, where this cosmic alchemy happened, was inside the hearts of stars. Deep within stellar cores, where temperatures reach tens of millions of degrees and pressures are beyond human comprehension. Lighter elements are fused together through nuclear reactions to create heavier ones. This process, called nucleosynthesis, is how stars spend their lives building up the periodic table. When those massive stars finally exhaust their fuel and die, they don't go quietly. They explode in spectacular supernovas, cosmic detonations so powerful, they briefly outshine entire galaxies. These explosions scatter the newly forged elements across space in vast expanding clouds. Billions of years later, some of that enriched material gathered into swirling nebulas, then condensed into new stars and planets, and eventually became part of living organisms here on Earth. You are not separate from the cosmos, merely observing it from the outside. You are made of it, woven from the same fabric as distant nebulas and alien worlds light years away. Every breath you take, every emotion you feel, is the universe experiencing itself through a temporary arrangement of stellar ash. In the most literal and poetic sense possible, you are stardust that learned to wonder about stars, cosmic recycled material that became conscious and looked back at its own origins with awe and curiosity. Light from the most distant galaxies has traveled for billions of years to reach your eyes. When astronomers point their powerful telescopes at the farthest reaches of space, they're not just seeing across unfathomable distances, they're actually looking backward through the river of time itself. Light travels at an astounding speed, roughly 300,000 kilometers every second, the fastest velocity possible in our universe according to Einstein's relativity. Yet even at this incredible pace, the cosmos is so unimaginably vast that photons from distant galaxies can spend billions of years journeying through the void before finally arriving at Earth. When you observe a galaxy that exists 10 billion light-years away, you are not seeing it as it appears today. You are witnessing it as it was 10 billion years ago, an era long before our Sun even existed, before Earth coalesced from cosmic dust, before the first simple microbes appeared in ancient oceans, before anything we would recognize as familiar came to be. The night sky is essentially a time machine, displaying the universe's history written in ancient photons. Those distant galaxies you see twinkling in deep space photographs may have changed dramatically since their light began its epic voyage toward us. Their stars may have lived entire lifetimes and died. The galaxies themselves may have merged with neighbors or been torn apart by gravitational forces. Some may have ceased to exist entirely, consumed by the inexorable expansion of space, or swallowed by monstrous black holes. Yet their light continues traveling faithfully through the darkness, ancient messengers carrying images from a cosmic past that can never return, showing us a universe that no longer exists in that form. The universe is expanding faster than the speed of light at its farthest edges. Einstein's special theory of relativity clearly states that nothing can travel through space faster than light. This cosmic speed limit is fundamental to physics and cannot be broken. But here is the fascinating exception that doesn't actually break the rule. Space itself has no such limitation. The fabric of the universe is stretching, pulling distant galaxies apart from each other. And at the very edges of the observable cosmos, this expansion happens faster than light can travel. This doesn't violate physics because the galaxies aren't actually moving through space at superluminal speeds. Instead, space itself is expanding between them, creating new distance where none existed before, like dots drawn on a balloon's surface separating as the balloon inflates. This fundamental property of our expanding universe has profound implications. It means there are regions of space we will never be able to see, no matter how long we wait or how advanced our technology becomes. There is a cosmic horizon beyond which light will never reach us, forever hidden by the relentless stretching of reality itself. Every moment that passes, more and more of the universe slips beyond this boundary, disappearing from view like ships sailing past the edge of an ocean. The expansion is accelerating too, driven by mysterious dark energy that permeates all of space. Galaxies that are currently visible to us will eventually recede so far and so fast that their light can no longer bridge the growing gap. Trillions of years in the future, if any conscious beings still exist, they will look up at a much lonelier night sky, seeing only their local cluster of gravitationally bound galaxies. With the rest of the universe having vanished beyond an unreachable horizon, there are more stars in the observable universe than grains of sand on every beach on Earth. Try to imagine all the beaches that exist on Owa planet. Every tropical shore where waves lap against white sand. Every rocky coastline where the ocean meets the land. Every desert expanse where dunes stretch to the horizon. Now imagine the impossible task of counting every single grain of sand from all these places combined. From the vast Sahara Desert to the beaches of Hawaii. From the endless shores of Australia to the windswept dunes of Arabia. That number would be staggering, almost beyond human comprehension. Scientists estimate there are roughly 7 quintillion, 500 quadrillion grains of sand on Earth. That is a 7, followed by 18 zeros. Your mind can barely grasp a number that large, yet incredibly astonishingly, there are more stars in the observable universe than all those grains of sand. Current astronomical estimates suggest there are approximately 200 billion trillion stars scattered across the cosmos. That is a 2 followed by 20, 3 zeros, Each and every one of those stars is a sun in its own right, a massive nuclear furnace converting hydrogen into helium, releasing tremendous amounts of energy, potentially warming its own family of planets, moons, asteroids, and comets. Some of those planets might harbor life. Civilizations might exist around distant suns, looking up at their own night skies, wondering if they're alone, asking the same questions we ask. The universe operates on scales that completely dwarf human comprehension, scales where billions become mere footnotes in cosmic calculations, and the concept of infinity feels closer than the horizon. We live in a cosmos of such staggering abundance that our minds struggle to contain it. Black holes warp the fabric of spacetime and can freeze time itself. Near a black hole, gravity becomes so monumentally intense that it doesn't just pull on matter with crushing force. It actually pulls on the fabric of spacetime, the fundamental structure of reality, distorting the very dimensions we move through. According to Einstein's general relativity, mass and energy curve spacetime, and objects moving through that curved space follow paths we perceive as gravitational attraction. But near a black hole's event horizon, that point of no return beyond which not even light can escape, spacetime becomes so severely warped that bizarre effects emerge. If you could somehow survive approaching a black hole's event horizon, something extraordinary would happen to time itself. For you, falling toward the black hole, time would seem to pass normally. But to someone watching from a safe distance far away, something impossible would appear to occur. They would see you moving slower and slower as you approach the event horizon, your movements becoming glacial, your clock ticking slower and slower relative to theirs. Eventually, from their perspective, you would appear to freeze completely, suspended forever at the edge of the black hole, never quite crossing the event horizon, your image growing dimmer and redder as light struggles to escape the intense gravity. This isn't science fiction or theoretical speculation. It is a real, measurable consequence of Einstein's equations, confirmed by countless observations and experiments. Black holes are not simply exotic objects floating in space. They are fundamental tiers in the cosmic fabric, places where the familiar rules of reality bend beyond recognition, twist into impossible shapes, and ultimately break down completely. They sit in the universe like existential question marks, dark and silent sentinels, warping everything around them, including the precious flow of time itself. At their cores, hidden behind the event horizon, all known physics collapses into mathematical singularities where our understanding fails utterly and new physics must emerge. The cosmic microwave background radiation is the afterglow of creation itself. Everywhere you look in the universe, in every possible direction you could point the most sensitive radio telescope, there exists a faint whisper of electromagnetic radiation. This radiation fills all of space uniformly. At a temperature barely above absolute zero, just 2.7 degrees Kelvin. This is the cosmic microwave background, the cooled remnant of the Big Bang itself. The birth cry of the universe, stretched and redshifted by nearly 14 billion years of relentless cosmic expansion. About 380,000 years after the universe began, in that initial singularity, it had expanded and cooled enough for a crucial transition to occur. Electrons and protons, which had been too energetic to bind together, finally combined into neutral hydrogen atoms. This moment, called recombination, made the universe transparent for the first time. Before this epoch, the cosmos was opaque, a thick hot plasma where photons couldn't travel far before being scattered by free electrons. But after recombination, light could suddenly travel freely through space, no longer constantly interacting with matter. That ancient light, released when the universe first became transparent, has been traveling through expanding space ever since. The expansion has stretched those photons from visible and infrared wavelengths into the microwave portion of the spectrum. When scientists mapped this radiation across the sky using satellites and ground-based instruments, They're seeing a baby picture of the universe, a snapshot of reality when it was still remarkably smooth and simple, before the first stars ignited their nuclear furnaces, before galaxies formed their majestic spiral arms. Before planets coalesced and life emerged. The cosmic microwave background contains tiny fluctuations, regions slightly warmer or cooler than average. These represent the seeds of all future structure, quantum fluctuations from the earliest moments of inflation stretched to cosmic scales. From these small irregularities, gravity would amplify density variations over billions of years, eventually creating the galaxies, clusters, and cosmic web we observe today. It is the oldest light we can possibly detect, a gentle electromagnetic glow from the very dawn of time itself, surrounding us always, filling the universe with whispers from creation. Neutron stars are so incredibly dense that a teaspoon of their material weighs 1 billion tons. Imagine taking a mass greater than our Sun, roughly 300,000 times the mass of Earth, and crushing it down into a sphere just 20 kilometers across, about the size of a medium city. That is a neutron star, one of the densest objects in the entire known universe. Matter compressed to a degree that utterly defies everyday intuition and experience. These bizarre stellar remnants form when massive stars, much larger than our Sun, finally exhaust all their nuclear fuel and undergo catastrophic gravitational collapse. The outer layers fall inward at significant fractions of the speed of light, rebounding off the incompressible core in a supernova explosion that briefly outshines the star's entire host galaxy. What remains is a core so dense that atomic structure itself completely breaks down under the pressure. Protons and electrons are literally crushed together, forced to merge and form neutrons, creating a state of matter that exists nowhere else in the universe, except possibly in the cores of these collapsed stars. A single teaspoon of neutron star material, if you could somehow scoop it up and transport it to Earth, would weigh approximately 1 billion tons. That is roughly equivalent to the mass of Mount Everest, concentrated into a volume you could hold in your hand. The gravity on a neutron star's surface is so monstrously powerful, it would flatten any ordinary object, any spacecraft or probe we could build, to literally atomic thickness. Some neutron stars spin at absolutely incredible rates, rotating hundreds of times per second, their surfaces moving at significant fractions of light speed despite the intense gravity trying to hold everything down. These rapidly rotating neutron stars, called pulsars, emit beams of electromagnetic radiation from their magnetic poles. As they spin like cosmic lighthouses, these beams sweep across space. When a beam happens to point toward Earth, we detect regular pulses of radiation with such precise timing that some millisecond pulsars rival atomic clocks in their regularity. Neutron stars represent physics at its most extreme. Matter and energy pushed to the very edge of what physical laws allow before collapsing further into black holes and disappearing from the universe entirely. Dark matter makes up most of the matter in the universe, yet remains completely invisible. Throughout the cosmos, galaxies spin at velocities that should tear them apart. Based on all the visible matter we can detect, all the stars glowing with light, all the gas clouds emitting radiation, there simply isn't enough mass to generate sufficient gravity to hold these structures together. The stars should fly apart like water flung from a spinning wheel. Yet galaxies remain intact, rotating smoothly and maintaining their shapes for billions of years, as if held together by invisible hands we cannot see. That unseen cosmic glue is dark matter, a mysterious form of matter that doesn't emit, absorb, or reflect electromagnetic radiation of any wavelength. It doesn't interact with light at all, making it completely invisible to all our telescopes, regardless of what part of the spectrum they observe. Dark matter reveals itself only through gravitational effects. By bending the paths of light from distant galaxies through gravitational lensing, by holding galaxy clusters together, and by influencing the rotation curves of spiral galaxies. It makes up approximately 85% of all matter in the universe, utterly dwarfing the ordinary atoms that compose stars, planets, and everything we can directly observe. Yet despite decades of increasingly sophisticated searches, we've never directly detected a single particle of dark matter. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, waiting for the rare interaction of a dark matter particle with ordinary atoms. So far, these experiments have found nothing conclusive. We don't know what dark matter is made of. Leading candidates include exotic particles that barely interact with normal matter, or perhaps modifications to our understanding of gravity itself on cosmic scales. Dark matter creates the invisible scaffolding upon which all visible cosmic structures form, a hidden architecture underlying everything we can see in the night sky. We know it exists because we can measure its gravitational influence precisely. We can map its distribution throughout the universe, but its fundamental nature remains one of the deepest mysteries in all of physics, a reminder that the universe we observe directly is merely a small fraction of what actually exists, and that most of reality remains hidden from our eyes. Time itself began with the Big Bang, and there was no before. Before the universe existed, before space expanded from a singularity, before matter and energy came into being, there was no before at all. This statement sounds paradoxical, almost nonsensical, but it reflects a profound truth about the nature of time itself. Time is not an eternal river that was always flowing through an infinite past. Time is part of the physical universe, woven together with space into the four-dimensional fabric called spacetime. Time had a beginning, a first moment when the cosmic clock started ticking, when causality began, when past and future first became meaningful concepts. This means the universe isn't infinitely old, stretching back through endless eons. It is approximately 13.8 billion years old, and every single moment of time that has ever existed, every second that has ever ticked by anywhere in the cosmos, fits within that vast but finite span. Asking what happened before the Big Bang is fundamentally meaningless, like asking what is north of the North Pole. The question assumes a framework of time and direction that doesn't exist beyond those boundaries. At the moment of the Big Bang, time itself came into existence along with space. There is no temporal framework in which to embed that initial moment, no earlier time from which it emerged. This has profound philosophical implications. It means the universe doesn't require a temporal cause in the traditional sense, because causation itself requires time, and time didn't exist until the universe began. We live inside time, unable to step outside it to view it objectively, forever trapped in the present moment that continuously flows from past to future, watching the universe unfold second by second, since that first inexplicable instant, when everything began from nothing, when time itself was born. Galaxies collide and merge in slow-motion cosmic dances over millions of years. The universe is vast almost beyond comprehension, filled with incomprehensible distances between stars and galaxies. Yet it is not static or unchanging. Galaxies drift through space on trajectories, determined by gravity and the expansion of the universe. And sometimes their paths intersect in spectacular cosmic encounters. When galaxies collide, the event unfolds in slow motion over timescales that make human history seem like an eye blink. These collisions don't happen like cars crashing on a highway. Galaxies pass through each other over tens or hundreds of millions of years, their component stars rarely making direct contact because the distances between individual stars within a galaxy are so enormous. The probability of any particular star hitting another star during a galactic merger is essentially zero. Stars are tiny points separated by vast gulfs of emptiness. But while the stars don't collide, the gravitational forces at work are tremendous and transformative. As two galaxies interact, their combined gravity pulls and reshapes both structures dramatically. Stars are flung into new orbits. Long tidal tails of stars stretch across millions of light years. Graceful arcs of matter pulled from the main bodies. Gas clouds compressed by the collision can trigger enormous bursts of new star formation, lighting up both galaxies with brilliant young blue stars. Supermassive black holes at the centers of both galaxies may eventually spiral together and merge, releasing tremendous amounts of energy in gravitational waves. Eventually, over hundreds of millions of years, the two separate galaxies blend into one larger structure, usually forming an elliptical galaxy. Our own Milky Way is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor located roughly 2.5 million light-years away. The two galaxies are approaching each other at about 110 kilometers per second. In approximately 4 to 5 billion years, they will begin their cosmic merger. When this happens, the night sky visible from Earth, if Earth still exists and has observers, will slowly transform. New constellations will emerge as stars from both galaxies mix. The process will continue for hundreds of millions of years until both become one larger, elliptical galaxy, sometimes whimsically called Milkomeda. It is a cosmic waltz choreographed entirely by gravity, played out over timescales so vast they make geological ages seem brief. There may be planets made almost entirely of diamond floating through space. Carbon is one of the most common elements created by dying stars through nuclear fusion. It is scattered throughout the universe in various forms. Under the right conditions of extreme pressure and temperature, carbon atoms arrange themselves into crystalline structures, forming the hardest naturally occurring material we know, diamond. Scientists have discovered exoplanets orbiting distant stars that may be composed primarily of crystalline carbon. One such world orbits a pulsar, the rapidly spinning remnant of a dead star. This planet, several times more massive than Earth, likely formed from the carbon-rich remains of a former companion star that was stripped away by the pulsar's intense radiation and gravitational forces. The conditions were perfect for the carbon to compress and crystallize. The result is a planet made largely of diamond, a cosmic gem roughly 5 times the size of Earth, sparkling silently in the void as it orbits its dead star companion. The surface would be unlike anything we've seen, crystalline formations covering the landscape. Light from the distant stars reflecting off faceted surfaces. It is an alien world that challenges our Earth-based expectations of what planets should be. These diamond worlds remind us that the universe's creativity and diversity exceed our wildest imaginings. Nature creates wonders we're only beginning to discover, treasures scattered across infinite space, too distant to ever physically reach or hold, existing in conditions too extreme for human exploration, but beautiful to contemplate from our safe distance. In the quiet depths of the cosmos, there are gems larger than worlds, monuments to the universe's chemical and physical diversity. Some ancient stars appear nearly as old as the universe itself, early in the development of modern cosmology. When scientists first began using observations of cosmic expansion to calculate the age of the universe, they encountered a perplexing problem. They discovered stars, particularly in globular clusters, orbiting our galaxy, that appeared to be older than their calculated age of the cosmos. This created an apparent paradox where children seemed older than their parent, suggesting either fundamental errors in understanding stellar evolution or serious miscalculations in determining the universe's age. This mystery persisted for years, troubling cosmologists and astrophysicists. Eventually, measurements were refined using better observations from satellites, studying the cosmic microwave background, improved understanding of dark energy's role in cosmic expansion, and more sophisticated computer models of how the universe evolved. The age of the universe was recalculated upward to approximately 13.8 billion years. Meanwhile, techniques for measuring stellar ages also improved. The oldest stars we've found are now measured at around 13 billion years old, fitting comfortably within cosmic history, with several hundred million years to spare. But this period of scientific uncertainty highlighted how much we still have to learn about the universe. These ancient stars, found in the spherical globular clusters that orbit our galaxy-like satellites, formed from the very first generation of matter, enriched enough to create stars. They're built almost entirely from hydrogen and helium, forged before significant amounts of heavier elements existed anywhere in the universe. They are cosmic elders, silent witnesses to nearly the entire history of existence. These stars have been shining for 13 billion years, virtually unchanged, while the universe evolved dramatically around them. Galaxies formed and merged. Our solar system came into being. Life emerged on Earth and evolved into countless forms. Human civilization rose from nothing. And through it all, these ancient suns burned steadily in the darkness, older than almost everything we can see. Quantum particles exist in multiple states simultaneously until observed. At the smallest scales of physical reality, far below the level of atoms and molecules, the universe behaves in ways that seem utterly impossible according to our everyday experience and common sense. Electrons, photons, and other subatomic particles don't exist in definite states or locations until they're measured or observed. Instead, they exist in strange quantum states called superposition, where they occupy multiple positions, possess multiple speeds, or exhibit multiple properties, all at the same time. This isn't simply a limitation of our measurement techniques or a reflection of our ignorance about where the particle really is hiding. It is a fundamental aspect of reality itself, confirmed by countless rigorous experiments performed over decades in laboratories around the world. Particles genuinely don't have definite positions, definite momenta, or definite properties until something interacts with them and forces them to choose, collapsing the quantum wave function into a single classical outcome. The famous double-slit experiment demonstrates this beautifully. Fire individual electrons one at a time at a barrier with two slits. Classical intuition says each electron goes through one slit or the other. But the results show something impossible. Each single electron somehow goes through both slits simultaneously, interfering with itself like a wave, creating an interference pattern that builds up over time. Only when you try to measure which slit the electron passes through does it behave like a particle going through just one. The act of observation fundamentally changes the outcome. This bizarre behavior underpins everything in the universe. It is not just a curiosity of physics labs. Quantum mechanics governs the chemical bonds that hold molecules together and make life possible. It drives the nuclear fusion reactions in stellar cores that create elements and power stars. It determines how electrons behave in semiconductors, enabling all modern technology. The universe at its deepest foundation is uncertain, probabilistic, and profoundly strange in ways that challenge every intuition we've developed through evolution and experience. The certainty and solidity we perceive in daily life is merely an illusion that emerges at larger scales, a classical facade built from countless quantum uncertainties that somehow average out to create the predictable world we inhabit. The universe might be infinite, extending forever in all directions without end. We can observe only a finite portion of the cosmos, strictly limited by fundamental physics. Light travels at a fixed speed, and the universe has a finite age. So there is a maximum distance from which light has had time to reach us since the Big Bang. This creates an observable universe, a sphere centered on Earth with a radius of about 46 billion light-years in all directions. But beyond that cosmic horizon, beyond the edge of what we can possibly see, the universe almost certainly continues. Current measurements from satellites studying the cosmic microwave background radiation suggest that space is geometrically flat on the largest scales we can measure. If this flatness extends beyond our observable bubble, if the universe truly has no curvature, then according to our best cosmological models, space could extend infinitely in all directions, going on and on without ever reaching an edge or boundary. This possibility is almost impossible for human minds to truly grasp. An infinite universe would contain infinite galaxies, infinite stars, infinite planets, and infinite instances of everything that can possibly exist. There would be infinite copies of you reading these exact words in galaxies trillions upon trillions of light years away, forever beyond our reach or detection. In an infinite universe, every possible arrangement of matter that doesn't violate physical laws must exist somewhere. Every possible history must play out. Every variation must occur. Infinity is not simply a very large number that you could eventually count given enough time. It is qualitatively different, a concept that breaks our finite minds. If the universe is truly infinite, then the ultimate questions about existence become even more mysterious. What does it mean for something to exist infinitely? How did infinite space come to be? These questions may forever remain beyond human understanding, reminders that reality extends far beyond the limits of our perception and comprehension. Space is completely silent because sound cannot travel through vacuum. On Earth, we're surrounded by sound constantly, voices speaking, music playing, wind rustling through leaves, waves crashing on shores. Sound is such a fundamental part of our experience that it is hard to imagine a world without it. But sound as we know it is a mechanical wave, a vibration of pressure traveling through a physical medium like air, water, or solid materials. Molecules bump into their neighbors, transferring energy and creating the compressions and rarefactions we detect as sound. In the near-perfect vacuum of space, there are so few particles per cubic meter that sound waves cannot propagate at all. There is no medium to carry the vibrations. Explosions, collisions, rocket engines firing at full thrust, stars exploding in violent supernovas, even the catastrophic mergers of black holes releasing more energy in seconds than the sun will produce in its entire lifetime. All of these incredibly violent and energetic events happen in utter, absolute silence. An astronaut working outside the International Space Station, floating in the void while Earth turns majestically below, experiences this profound quiet. It is a silence deeper and more complete than any soundproofed room on Earth could achieve. The only sounds they hear are transmitted through their spacesuit by physical vibration, their own breathing, the mechanical systems keeping them alive, and voice communications from mission control transmitted through radio waves converted to sound by their equipment. It is a stark and sometimes unsettling reminder that space is an environment utterly unlike our home planet, a place where familiar rules and expectations don't apply. The universe unfolds its grand cosmic drama in absolute silence, vast and indifferent to any observers, a theater where light and gravity are the only messengers carrying information across the gulfs between worlds, and where sound is forever forbidden from traveling through the empty void. Stars are born continuously in vast clouds of gas and dust spanning light years. Scattered throughout every galaxy are enormous nebulae, immense clouds composed primarily of hydrogen and helium gas, mixed with tiny grains of cosmic dust. These clouds can span hundreds or even thousands of light years across, regions so vast that light itself takes centuries to traverse them from one side to the other. They contain enough raw material to create thousands or even millions of stars. When illuminated by radiation from nearby young stars, these nebulae glow in spectacular colors, appearing as beautiful cosmic tapestries in telescope images, painted in shades of red from hydrogen emission, blue from scattered starlight, and dark lanes where dense dust blocks light. But these gorgeous clouds are far more than just pretty pictures. They are stellar nurseries, cosmic wombs, where new generations of stars are constantly being born through gravitational collapse. The process begins when something disturbs the delicate equilibrium of a gas cloud. Perhaps a shock wave from a nearby supernova explosion compresses part of the cloud. Perhaps two clouds collide in space. Perhaps the cloud simply becomes dense enough that its own gravity overcomes the outward pressure of its temperature. Whatever the trigger, regions within the nebula begin collapsing under their own weight. As material falls inward toward the center of these collapsing regions, gravitational potential energy converts to heat. The temperature rises, the pressure increases. More matter continues falling in, drawn by the strengthening gravitational pull. Eventually, after perhaps 1 million years of collapse, the center becomes hot and dense enough that hydrogen nuclei moving at tremendous speeds overcome their electrical repulsion and fuse together, forming helium and releasing enormous amounts of energy, according to Einstein's mass-energy equivalence. Nuclear fusion ignites. A new star is born, beginning its life on what astronomers call the main sequence, where it will spend most of its lifetime steadily converting hydrogen to helium. This process is happening right now in regions like the Orion Nebula, easily visible to the naked eye as a fuzzy patch in the Sword of Orion constellation. Inside that glowing cloud, new stars are emerging from darkness at this very moment, lighting up the surrounding gas with their fierce radiation, blowing away the remaining material with powerful stellar winds, beginning their journeys through billions of years of existence. Stars are not eternal fixtures that have always existed unchanged. They have births, lives measured in millions or billions of years, and deaths that return their enriched material to space to form new generations in an endless cycle of cosmic recycling. Our Sun loses over 4 million tons of mass every single second through fusion. That familiar yellow star hanging in our daytime sky, the sun that warms our planet and makes all life on Earth possible, constantly converts its own mass into pure radiant energy through nuclear fusion reactions in its core. Following Einstein's revolutionary equation, E=mach², which reveals the fundamental equivalence of mass and energy, the Sun transforms approximately 4 million tons of its mass into light and heat every second. To put that in perspective, that is roughly equivalent to 4,000 fully loaded aircraft carriers being converted entirely into energy every single second. This might sound catastrophic and unsustainable, like the Sun is rapidly consuming itself and will soon burn out, leaving us in frozen darkness. But the Sun's total mass is so enormously, unimaginably vast, approximately 2 followed by 30 zeros kilograms, that it can sustain this continuous loss for billions upon billions of years without significant consequences to its structure or output. The warm sunlight you feel on your skin during the day, the light that drives photosynthesis in every plant and feeds the entire food chain, the energy that powers Earth's weather systems and ocean currents, all of it represents the Sun slowly spending itself, radiating its very essence away into the void of space as electromagnetic energy traveling at light speed in all directions. Over the Sun's entire main sequence lifetime of roughly 10 billion years, it will lose only a tiny fraction of its total mass through fusion, perhaps a few tenths of a percent. But that small sacrifice, that patient conversion of hydrogen into helium and mass into energy, is more than enough to illuminate the entire solar system and make a blue-green planet teem with abundant life for billions of years. It is a slow, steady, patient burn that has continued uninterrupted for 4.6 billion years and will continue for approximately 5 billion more before the Sun finally exhausts the hydrogen fuel in its core and begins its transformation into a red giant star, eventually ending its life as a slowly cooling white dwarf. There are rogue planets drifting alone through the darkness between stars. When we think about planets, we naturally picture them orbiting stars in organized solar systems like our own. But the cosmos is far stranger and more diverse than our limited experience suggests. Not all planets orbit stars in stable systems. Some worlds have been violently ejected from their parent star systems during the chaotic early days of planetary formation. Gravitational interactions during close encounters with larger planets can slingshot smaller worlds outward at tremendous velocities, flinging them into interstellar space. These orphaned worlds, called rogue planets or free floating planets, drift through the galaxy completely alone, untethered to any star, traveling through the cold darkness between solar systems on trajectories that may never bring them near another star for billions of years. Without a sun to warm them or provide energy, a rogue planet's surface would be unimaginably cold and dark, with temperatures approaching absolute zero. darker than the darkest night on Earth, colder than the coldest winter anywhere on our world. No sunlight would ever break the eternal darkness. No seasons would mark the passage of time. These worlds seem utterly dead and inhospitable. Yet some rogue planets might not be completely frozen and lifeless. Those with substantial mass might retain residual heat from their original formation, heat trapped in their interiors from the gravitational energy of accretion. Radioactive decay of elements in their cores could provide additional warmth for billions of years. If a rogue planet is large enough and has a thick atmosphere, this internal heat might be sufficient to maintain liquid water in subsurface oceans, sealed beneath kilometers of ice, completely isolated from any external energy source. Tidal heating from large moons could provide additional energy. In such hidden oceans, completely cut off from any star's light, life might theoretically exist, sustained entirely by chemical energy from hydrothermal vents, similar to the ecosystems found around deep-sea vents on Earth, that thrive without any sunlight. Recent observations using gravitational microlensing, where a massive object's gravity briefly magnifies the light from a background star, suggest there could be billions or even trillions of rogue planets wandering through our Milky Way galaxy alone. They vastly outnumber the stars themselves. These silent nomads drift through cosmic night invisible and undetected, except for those rare moments when they pass in front of a distant star and briefly bend its light through gravitational lensing. They remind us that the universe contains endless unexpected phenomena, entire categories of worlds we never imagined, planetary orphans cast out into eternal darkness, drifting through the void for billions of years on journeys without destination. Light itself can be bent and distorted by gravity, according to relativity. Isaac Newton's classical physics described gravity as a force of attraction between masses, acting instantaneously across space. But Einstein's general theory of relativity revealed something far more profound and strange. Massive objects don't simply pull on other objects. They actually warp and curve the fabric of spacetime itself, like a bowling ball creating a depression in a stretched rubber sheet. Everything in the universe, from tiny particles to beams of light, follows the curvature of this warped spacetime. Light always travels in straight lines through space, but when space itself is curved by gravity, those straight paths bend and curve along with it. This phenomenon, called gravitational lensing, has been confirmed through countless observations and has become an invaluable tool for astronomers studying the universe. When light from a very distant galaxy travels across billions of light-years of space and passes near a massive object, like a galaxy cluster positioned between us and that distant light source, the cluster's immense gravity bends the light's path. Sometimes this bending creates multiple distorted images of the same background galaxy, appearing at different positions in the sky. Sometimes it produces bright arcs or partial rings around the lensing object. In cases of near-perfect alignment, called Einstein rings, a distant galaxy can be smeared into a complete circle surrounding the lensing mass. This gravitational bending allows astronomers to see objects that would otherwise be completely hidden behind intervening matter. It also lets them measure the total mass of the lensing object, including the invisible dark matter that doesn't emit any light, but still contributes to the gravitational field and affects how light bends. Some of the most distant galaxies ever observed are only visible because their light has been magnified and brightened by gravitational lensing from massive clusters in the foreground. Gravity doesn't just pull on physical matter that has mass. It reshapes light itself, the massless photons that carry energy and information across the cosmos, curving the very paths these particles of light travel through space, turning the universe into an enormous complex hall of mirrors where distant objects can appear in unexpected places, distorted and magnified by the invisible warping of spacetime itself. The universe has no center, and every location is equally valid. Our everyday experience and intuition strongly suggest that explosions happen at specific locations and expand outward from that central point. So it is completely natural and reasonable to imagine the Big Bang as a massive explosion that occurred at a particular point in space billions of years ago, with the universe expanding outward from that origin like a bomb going off. But this mental picture, as intuitive and reasonable as it seems, is fundamentally incorrect and misleading. The Big Bang didn't happen at a particular location within space. It happened everywhere simultaneously, throughout all of space at once. Every single point in the universe today, every location you could possibly identify or travel to, was once part of that initial ultra-dense, ultra-hot state. Space itself came into existence with the Big Bang and has been expanding ever since. There is no center from which everything is expanding, no special cosmic location that can claim to be the origin point of the universe. When we observe distant galaxies moving away from us in all directions, receding faster the farther away they are, it is not because we happen to be located at some privileged central position. Observers in any of those distant galaxies would see exactly the same thing from their perspective. All other galaxies receding from them in every direction, each observer seemingly at the center of cosmic expansion. There is no privileged location anywhere in the universe, no cosmic downtown or metropolitan center, no place more important or more central than anywhere else. The universe is homogeneous and isotropic on the largest scales, meaning it looks essentially the same in all directions and at all locations when you average over volumes larger than galaxy clusters. This is called the cosmological principle, and it is supported by observations of the cosmic microwave background and the large-scale distribution of galaxies. We are all simultaneously at the center of our own observable universe, the sphere of space from which light has had time to reach us. And yet nowhere is truly the middle or the edge of the whole infinite or near. Infinite cosmos. It is a perspective that is both humbling and democratizing, suggesting that our location is both supremely important as our unique viewpoint and utterly typical as just another place in an incomprehensibly vast universe. Cosmic rays pass through your body constantly from distant space. Right now, as you rest quietly and listen to these words, your body is being bombarded by high-energy particles from space. These cosmic rays, despite their misleading name suggesting electromagnetic radiation, are actually atomic nuclei that have been stripped of their electrons, traveling through space at velocities approaching the speed of light. Most cosmic rays are protons, hydrogen nuclei, though some are heavier elements like helium, carbon, or even iron. They originate from some of the most violent and energetic processes in the universe. Supernova explosions thousands of light years away, the intense magnetic environments near rapidly spinning neutron stars, the powerful particle acceleration near supermassive black holes, and active galactic nuclei where tremendous amounts of matter spiral into the cosmic abyss. These particles have traveled across the galaxy for millions or even billions of years through the vast empty darkness between stars, before randomly intersecting with Earth and passing through your body. Earth's magnetic field deflects many of these charged particles away from our planet, channeling them toward the poles where they interact with the upper atmosphere and create beautiful auroras. The atmosphere itself absorbs and breaks apart most of the remaining cosmic rays in cascades of secondary particles high above the surface. But some cosmic rays, particularly the most energetic ones with truly staggering amounts of kinetic energy, make it all the way through the atmosphere to ground level and pass directly through you. Right now, at this very moment, hundreds or possibly thousands of these particles are zipping through your body every second at nearly light speed, passing harmlessly through tissue and bone and organs, leaving virtually no trace of their passage, completely undetected by your senses. Each one is a messenger from distant cosmic catastrophes, carrying information encoded in its energy and composition about the violent events that accelerated it to such tremendous speeds. You are continuously bathed in this invisible radiation from distant stars and galaxies, a constant physical reminder that we are not isolated from the wider universe, but intimately connected to it through countless processes, touched by the cosmos in ways we never consciously perceive. or acknowledge. Some galaxies are cosmic cannibals that consume their smaller neighbors. In the universe, size often determines survival. Large galaxies grow even larger by gravitationally capturing and slowly absorbing smaller neighboring galaxies in violent mergers that unfold over hundreds of millions of years. Our own Milky Way has absorbed dozens of smaller dwarf galaxies over its long evolutionary history, tearing them apart with relentless tidal forces and incorporating their stars into its own expanding structure. Streams of stars from these ancient mergers still wrap around the Milky Way like faint ghostly rivers, evidence of past cosmic meals, and the process continues today. The Milky Way is currently in the act of devouring several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which is being slowly shredded and dissolved by our galaxy's gravity. Its stars are being scattered in long streams that loop around the Milky Way multiple times, gradually mixing into our galaxy's outer halo. When a large galaxy's enormous gravitational field captures a smaller companion, the smaller galaxy cannot escape. Tidal forces, the same type of gravitational effects that create ocean tides on Earth, but operating on a cosmic scale, stretch and distort the smaller galaxy. Stars on the near side feel stronger gravity than those on the far side. This difference pulls the galaxy apart over time. Its stars are scattered and absorbed into the larger galaxy's structure and halo. Gas and dust from the smaller galaxy may be funneled toward the central regions of the larger one, compressed by gravitational forces, sometimes triggering intense bursts of new star formation that light up both galaxies with brilliant young blue stars. The supermassive black holes at the centers of both galaxies may eventually spiral together, orbiting each other in an ever-tightening dance, releasing tremendous amounts of energy in gravitational waves before finally merging into a single larger black hole. This process of galactic cannibalism is common throughout the universe and represents one of the primary ways that galaxies grow and evolve over billions of years of cosmic time. Galaxies are not static, isolated island universes floating peacefully and unchanging in space. They are dynamic, evolving structures that constantly interact, merge, collide, and consume each other, growing larger and more complex through these violent encounters. The Milky Way itself will one day be consumed when it merges with the Andromeda Galaxy. In approximately 4 billion years, the two galaxies will mix their stars in a slow cosmic embrace lasting hundreds of millions of years, eventually forming a single large elliptical galaxy. In the cosmos, survival often means becoming part of something bigger, losing individual identity to create new larger structures in an endless process of growth and transformation. Time flows at different rates depending on gravity and motion. Newton's classical physics assumed that time was absolute and universal, flowing at the same steady rate everywhere in the universe for all observers regardless of their motion or location. But Einstein's theories of relativity shattered this comfortable assumption and revealed that time is far stranger and more flexible than anyone had imagined. General relativity shows that gravity affects not just the trajectories of objects moving through space, but the very flow of time itself. The stronger the gravitational field at a particular location, the slower time passes there, relative to regions with weaker gravitational fields. This isn't a minor theoretical quirk with no practical consequences. It is a real measurable effect that must be accounted for in modern technology. On Earth's surface, where gravity is relatively strong, time moves measurably slower than it does high above the planet in orbit, where gravity is weaker. The difference is incredibly tiny, just a few microseconds, per Dalton U, far too small for human senses to detect directly. But it is large enough that the global positioning system satellites orbiting Earth must account for this relativistic time dilation in their calculations to maintain the precision necessary for accurate navigation. The atomic clocks aboard GPS satellites tick slightly faster than identical clocks on Earth's surface, because they're in a weaker gravitational field. If this difference wasn't corrected, GPS navigation would accumulate errors of several kilometers per Dalton U, making the system useless. Near a black hole's event horizon, where gravity becomes monstrously intense, approaching infinite strength, this effect becomes dramatic and extreme. Time can slow to a near standstill relative to distant observers. An hour experienced near the event horizon of a massive black hole could correspond to years, decades, or even centuries passing in the outside universe far from the gravitational well. Astronauts orbiting a black hole would age much more slowly than people remaining far away. In the cosmos, time is not a universal constant ticking away uniformly everywhere. It is flexible and elastic, flowing faster or slower depending on the local gravitational environment and the relative motion of observers. The universe doesn't have a single master clock keeping absolute time for everything. Instead, it has countless individual time streams, each flowing at its own pace determined by local conditions, all equally valid from their own reference frame, none more correct or fundamental than any other. Even the vacuum of space isn't truly empty at the quantum level. Classical physics suggested that if you could somehow remove all matter and energy from a region of space, creating a perfect vacuum, you would be left with absolutely nothing, a void containing zero energy and zero activity. But quantum mechanics reveals that this classical picture is fundamentally wrong. Even in the darkest, most remote regions of intergalactic space, far from any stars or galaxies, in voids that seem to contain absolutely nothing by any classical measure, quantum mechanics ensures that the vacuum is never completely and truly empty. The vacuum state is not nothing. It is the lowest energy state of all the quantum fields that pervade space. And even in this ground state, the fields fluctuate. Virtual particles and their corresponding antiparticles constantly pop into existence spontaneously as quantum fluctuations, appearing out of nothing in matter, antimatter pairs, borrowing energy from the vacuum itself, existing in apparent violation of energy conservation for incredibly brief intervals of time, then annihilating each other and disappearing back into the vacuum before the universe notices the energy debt. These virtual particles exist for time periods so short that Heisenberg's uncertainty principle permits the temporary energy violation. This quantum foam is a seething sea of activity at the smallest scales, invisible and intangible to us and our instruments. Yet fundamental to the nature of reality itself, the energy of these vacuum fluctuations has measurable physical effects. The Casimir effect demonstrates this beautifully. Two uncharged metal plates placed very close together in a vacuum experience an attractive force because the vacuum fluctuations between the plates, restricted by the narrow gap, differ from the unrestricted fluctuations outside, creating a net pressure that pushes the plates together. This has been measured precisely in laboratories. The vacuum is far from empty nothingness. It is alive with quantum possibility, permeated by fields, filled with virtual particles flickering in and out of existence billions of times. Percy Cond, a dynamic substrate of potential energy that underlies all physical reality. What appears to our eyes and classical instruments as perfect emptiness is actually an ever-changing foundation from which actual particles can emerge and into which they can disappear. The quiet quantum hum of existence at its most fundamental level. Pulsars are nature's most precise cosmic clocks spinning hundreds of times. Percy Cond. When a massive star many times the sun's mass reaches the end of its life and exhausts all possible nuclear fuels, it can no longer generate enough outward pressure to support itself against its own gravity. The core undergoes catastrophic gravitational collapse in a fraction of a second, rebounding in a supernova explosion that tears the star apart. What remains in some cases is an incredibly dense neutron star, a stellar corpse composed almost entirely of neutrons packed together at nuclear density. Conservation of angular momentum means that as the core collapses from a star hundreds of thousands of kilometers across down to a sphere just 20 kilometers in diameter, it spins faster and faster, like a figure skater pulling in their arms during a spin. Some neutron stars rotate hundreds of times, per surfaces moving at significant fractions of light speed, despite the crushing gravity. If the neutron star has a strong magnetic field misaligned with its rotation axis, it acts like a cosmic lighthouse. Charged particles accelerated by the intense magnetic field emit beams of electromagnetic radiation from the magnetic poles. As the neutron star spins, these beams sweep through space. If one of those beams happens to sweep past Earth during each rotation, we detect regular pulses of radiation with astonishing precision and regularity. These objects, called pulsars, are among the most accurate clocks in the entire universe. The most stable millisecond pulsars vary in their rotation period by less than a microsecond over years of observation, revealing or even exceeding the precision of the best atomic clocks ever built by humans. Astronomers use pulsars as cosmic timekeepers and fundamental calibration sources. Arrays of pulsars spread across the galaxy are being used to detect gravitational waves passing through our region of space by looking for tiny correlated variations in pulse arrival times. These stellar remnants have even been proposed as navigational beacons for future interstellar travel. Natural reference points whose rhythms could help spacecraft determine their position anywhere in the galaxy. In the midst of cosmic chaos, randomness, and unpredictability, pulsars are remarkable islands of order and precision. Stellar metronomes beating with mechanical regularity for millions of years, marking time with extraordinary faithfulness. The universe is getting progressively colder as it expands into the far future. In the earliest moments after the Big Bang, the universe was unimaginably hot, with temperatures exceeding trillions of degrees, far hotter than the cores of the most massive stars. Space itself glowed with intense radiation. But as the universe expanded, that primordial heat spread out over an ever-increasing volume of space, like a fixed amount of thermal energy distributed through a growing container. The average temperature everywhere dropped continuously as expansion proceeded. Now, nearly 14 billion years later, the average temperature of intergalactic space is approximately 2.7 degrees Kelvin, just barely above absolute zero, the coldest temperature theoretically possible, where all thermal motion ceases. That is cold almost beyond comprehension, far colder than the coldest winter on Earth, colder than liquid nitrogen, approaching the fundamental limit where atoms barely vibrate. And the universe continues expanding, driven by mysterious dark energy, so temperatures will keep dropping. As cosmic expansion continues accelerating into the incomprehensibly distant future, the universe will grow even colder still. Eventually, after trillions upon trillions of years, far longer than the current age of the cosmos, the last generation of stars will exhaust their nuclear fuel and burn out. No new stars will form because all available gas will have been locked up in stellar remnants or dispersed too thinly by expansion. Galaxies will fade from brilliant spirals and majestic ellipticals to dark collections of stellar corpses, white dwarfs, neutron stars, and black holes drifting through the void. The cosmos will continue cooling inexorably, approaching ever closer to absolute zero, but never quite reaching it. Eventually, the universe will approach a final state physicists call heat death, a condition of maximum entropy, where no energy gradients remain anywhere. No differences in temperature exist between any two regions, no fuel remains to power any processes, and nothing meaningful can happen anymore. It is a fate almost incomprehensibly far in the future, so distant that the entire current age of the universe is barely a moment in comparison. But given what we understand of physics and cosmology, it appears inevitable. The universe is on a one-way journey toward increasing entropy and disorder, gradual cooling and fading, and ultimate stillness and darkness. a slow cosmic wind down toward an eternal frozen night where even the longest-lived black holes have finally evaporated through Hawking radiation. And nothing remains but an infinitely thin soup of particles, growing ever colder in the endless dark. Some of the most massive stars explode so violently, they leave nothing behind. When truly enormous stars, those born with masses exceeding perhaps 100 times our Sun, reach the end of their short, intense lives, they can die in explosions so catastrophically powerful that they obliterate themselves completely, leaving no remnant whatsoever. These rare events, called pair instability supernovas, occur when a star's core becomes so incredibly hot that the gamma-ray photons in the core have enough energy to spontaneously transform into particle-antiparticle pairs, specifically electrons and positrons. This process suddenly removes energy from the core in the form of particle mass, robbing the core of the radiation pressure that was supporting it against gravitational collapse. Without that support, the core collapses catastrophically, heating up even more, producing more gamma rays, creating more particle pairs in an unstoppable runaway process. The collapse triggers a thermonuclear explosion so violent and complete that it tears the entire star apart. Every layer gets blasted into space at tremendous velocities. No neutron star or black hole is left behind. No compact remnant remains. The star gives everything back to the cosmos. It is total annihilation, a complete transformation from a massive organized star into an expanding cloud of gas enriched with heavy elements, dispersing into the interstellar medium to eventually become part of new generations of stars and planets. For a few weeks, such an explosion can outshine an entire galaxy of hundreds of billions of normal stars. Then it fades, leaving behind only expanding debris and the memory of what was once the brightest object in that region of space. These explosions are rare because stars massive enough to die this way are themselves rare, and they live very short lives of only a few million years before ending catastrophically. But when they occur, they represent the ultimate stellar sacrifice. A star giving absolutely everything it has back to the universe, leaving behind only the elements it created during its brief, fierce life, and the light from its spectacular death, expanding outward into the cosmos forever. The universe might undergo endless cycles of expansion and contraction. The standard cosmological model suggests the universe began with the Big Bang, has been expanding ever since, and will continue expanding forever, eventually reaching heat death in the incomprehensibly distant future. But this may not be the only possibility. Some speculative cosmological models propose that the universe could be cyclical, undergoing endless repetitions of expansion and contraction, birth and death, in an eternal cosmic rhythm. In these scenarios, after the current expansion phase continues for trillions of years and the universe grows cold and dark, some mechanism might eventually cause the expansion to slow, stop, and reverse. Gravity might begin pulling everything back together. The universe would enter a contraction phase, all the matter and energy drawing closer together over billions or trillions of years. Galaxies would begin approaching each other rather than receding. The cosmic microwave background radiation would blue shift rather than red shift, growing hotter as space contracted. Eventually, everything would collapse back together in a big crunch, the opposite of the Big Bang, all matter and energy compressed back into an infinitely dense, infinitely hot state. But instead of that being the end, the Big Crunch could somehow trigger another Big Bang, initiating a new cycle of expansion. The universe would be reborn, expanding again from the singular state, possibly with different physical constants, different laws of physics, different fundamental particles. This new universe might be utterly unlike our own, or it might be similar, or it might be identical if the physics resets to the same initial conditions. This oscillating universe model is highly speculative and faces serious theoretical challenges. Current observations suggest the expansion is accelerating rather than slowing, driven by dark energy, which would prevent any future contraction. But some theorists propose mechanisms by which dark energy might change its properties over cosmic timescales, or new physics might emerge. If the cyclic model is correct, our universe might be just one cosmic breath in an eternal cycle of breathing, one chapter in an infinite book, a single iteration in an endless series of universes, each rising from the ashes of the previous one. It is a vision of cosmic eternality, where the universe never truly began and will never truly end, but cycles forever through births and deaths, each cycle potentially unique, an endless sequence of cosmic reincarnations, stretching infinitely into the past and infinitely into the future. Gravitational waves are ripples in spacetime itself, traveling at light speed. Einstein's general relativity predicted that accelerating masses should produce ripples in the fabric of spacetime, disturbances that propagate outward through the universe at the speed of light, carrying energy and information about the events that created them. For decades, this remained a theoretical prediction with no direct observational confirmation. Then, in September 2015, the LIGO Observatory made history by directly detecting gravitational waves for the first time, opening an entirely new window on the universe. The detected waves came from two black holes, each roughly 30 times the mass of the Sun, spiraling into each other in a cosmic death dance, 1.3 billion light-years away. As they orbited ever faster and closer together, they generated gravitational waves that spread outward in all directions. When these waves finally reached Earth after traveling for more than 1 billion years, they were incredibly faint, stretching and squeezing space itself by less than 1/10,000th the diameter of a proton. Yet, LIGO's incredibly sensitive laser interferometers detected this tiny distortion, measuring the gravitational wave signal with extraordinary precision. The detection confirmed Einstein's century-old prediction and marked the beginning of gravitational wave astronomy. Since that first detection, dozens more gravitational wave events have been observed, merging black holes of various masses, colliding neutron stars that also produced electromagnetic signals observed by conventional telescopes, and possibly other exotic sources. These observations provide information about cosmic events that are invisible or difficult to study with conventional telescopes. Gravitational waves can travel through anything without being absorbed or scattered, so they carry pristine information from the hearts of the most violent events in the universe: black hole mergers, neutron-star collisions, possibly even the Big Bang itself. The universe is ringing like a bell struck by cosmic catastrophes, and we've finally developed the ability to hear those subtle vibrations in spacetime, opening our ears to a cosmic symphony we never knew existed. There may be more dimensions of space than the 3 we experience. Our everyday experience gives us 3 spatial dimensions: length, width, and height. We can move forward, backward, left, right, and up, down. This 3-dimensional space seems fundamental and complete, the entire stage on which reality plays out. But various advanced theoretical physics models, particularly string theory and its extensions, suggest that additional spatial dimensions might exist beyond the 3 we perceive directly. These hypothetical extra dimensions could be curled up or compactified so incredibly small, perhaps near the Planck length of 10 circumflex -35 meters, that we can't detect them with any current or foreseeable technology. Alternatively, they might be large, but we're somehow confined to a 3-dimensional membrane or brain floating in a higher dimensional space, unable to access or perceive the extra dimensions directly. If extra dimensions exist, they could help explain profound mysteries in physics. They might account for why gravity is so much weaker than the other fundamental forces. Perhaps gravity can leak into extra dimensions while other forces are confined to our 3-dimensional space. They could explain the nature of dark matter. Perhaps it is ordinary matter existing in extra dimensions, affecting us only through gravity, which propagates through all dimensions. Extra dimensions might provide a framework for unifying quantum mechanics and general relativity, the holy grail of theoretical physics. While these ideas remain highly speculative and unproven, they push the boundaries of how we conceptualize reality itself. The universe we see and experience directly might be merely a shadow, a limited low-dimensional projection of a far richer, more complex reality existing in dimensions beyond our perception or comprehension. realms our senses cannot access and our brains cannot visualize. Realities that exist alongside us yet forever remain hidden from direct observation. Stars appear to twinkle because of Earth's turbulent atmosphere. When you look up at the night sky, stars seem to flicker and dance, their brightness and even their apparent positions shifting slightly from moment to moment. This twinkling, called astronomical scintillation, seems like a property of the stars themselves, but it is actually caused entirely by Earth's atmosphere. As starlight travels through the near vacuum of space, it moves in essentially straight lines at constant brightness. But when it enters Earth's atmosphere and travels through the final 100 kilometers to reach the ground, it passes through air layers with different temperatures and compositions, all in constant turbulent motion. These variations in the atmosphere's refractive index cause the light to bend slightly in random directions that change from moment to moment. The star's apparent position shifts slightly. Sometimes atmospheric turbulence focuses the light, making the star briefly brighter. Other times, it defocuses the light, making the star dimmer. The result is the familiar twinkling we see, which is actually atmospheric distortion, not anything happening to the star itself. In space above the atmosphere, astronauts aboard the International Space Station see a completely different view. Stars shine with absolutely steady, unwavering light, their positions fixed, their brightness constant. No twinkling occurs because there is no atmosphere to distort the light. This atmospheric blurring is one of the main reasons astronomers build telescopes on high mountains, in deserts with calm air, and increasingly in space. Adaptive optics systems in modern ground-based telescopes try to correct for atmospheric distortion in real time by measuring the wavefront distortions and using deformable mirrors to cancel them out. The twinkling of starlight is beautiful and romantic, inspiring countless poems and songs throughout human history. But it is also a reminder that we view the universe through a veil, a turbulent ocean of air that softens and distorts the cosmos above, showing us a slightly blurred and dancing version, rather than the crisp reality that exists beyond our atmospheric cocoon. Some galaxies emit almost no visible light and hide in darkness. When we think of galaxies, we picture brilliant collections of stars, majestic spirals with glowing arms, dense ellipticals blazing with the light of trillions of old stars, irregular dwarf galaxies studded with bright young stars. But not all galaxies shine visibly. Some galaxies, called dark galaxies, contain very few stars or none at all, composed primarily of gas and the mysterious invisible dark matter that dominates their mass. They don't emit significant visible light, making them incredibly difficult to detect and study. Astronomers find these ghost galaxies indirectly, by observing how they absorb light from more distant background objects, or by detecting faint emissions in radio wavelengths from their hydrogen gas, or by observing their gravitational effects on nearby visible galaxies. These dark galaxies challenge our understanding of how galaxies form and evolve. Why did they fail to convert their gas into stars like most galaxies do? Perhaps they exist in environments where conditions never became right for significant star formation. Perhaps they lost their gas to more massive neighbors. Perhaps we're catching them in an early evolutionary stage before stars form. Or perhaps there is something about the properties of dark matter in these systems that prevents sufficient star formation through mechanisms we don't yet understand. Whatever the explanation, these ghostly galaxies remind us that the visible universe we observe directly is incomplete, that much of cosmic structure remains hidden in darkness. Dark galaxies are shadows in the cosmic web, invisible participants in the universe's gravitational structure, affecting the motions of visible galaxies and shaping the large-scale distribution of matter through their gravity alone, while remaining almost entirely dark, undetectable except through the most subtle observational techniques. The Big Bang was not an explosion that happened at a point in space. Despite the name suggesting a massive detonation, and despite countless illustrations showing the universe expanding outward from a central point, the Big Bang was fundamentally different from any explosion we experience or can easily visualize. It wasn't an explosion of matter and energy into pre-existing empty space. It was the sudden expansion of space itself, carrying matter and energy along with it. Every point in the current universe was part of the initial singularity. There was no outside, no void into which the universe exploded. Space and time began together in that moment. You cannot ask what happened before the Big Bang because time itself didn't exist before that moment. The question is meaningless, like asking what is north of the North Pole. The expansion is often misunderstood as galaxies flying apart through static space. That is not accurate. Space itself is stretching, creating new distance between objects that are actually at rest relative to their local spacetime. Imagine dots drawn on a balloon's surface. As you inflate the balloon, every dot moves away from every other dot. Not because the dots are moving across the rubber surface, but because the surface itself is expanding. No dot is at the center of the expansion. From any dot's perspective, all other dots appear to be moving away. The universe works the same way in 3 dimensions. This concept is profoundly difficult to visualize because we're used to thinking of explosions as events happening within space, starting at a point and expanding into surrounding emptiness. But the Big Bang was the birth of space itself, an event that defies ordinary analogies and intuitions, describable mathematically, but nearly impossible to picture accurately in our minds. Some planets orbit binary star systems, experiencing double sunsets. Most planets in our solar system orbit a single star, the Sunday. For most of human history, we assumed this was the standard configuration. But as astronomers discovered thousands of exoplanets orbiting other stars, they found tremendous diversity, including planets in circumbinary orbits, worlds that orbit 2 stars simultaneously. These planets, sometimes called Tetoian, like after the fictional planet in Star Wars, experience complex gravitational dynamics as they orbit their twin suns. The 2 stars orbit each other in a binary system, sometimes quite close together, sometimes separated by larger distances. The planet orbits both stars from farther out, tracing a complex path through the constantly shifting gravitational field created by the moving stellar pair. Such systems were once thought to be rare or unstable, unlikely to form or maintain planets. But observations from telescopes like Kepler have revealed them more common than expected. Many stable circumbinary planets have been discovered. Imagine standing on the surface of such a world. You would see 2 suns in the sky, perhaps different colors if they're different types of stars, casting overlapping shadows, creating unique lighting that changes as the stars orbit each other. Depending on the orbital configuration, you might witness spectacular double sunsets where 2 suns sink below the horizon, one after the other, or simultaneously, painting the alien sky in dual hues and creating shadow patterns impossible on Earth. The seasons would be complex and unpredictable, influenced by the changing distances to both stars as they orbit each other and as the planet orbits them. It is a reminder that solar systems come in endless varieties, each more strange and wonderful than we previously imagined. Configurations of stars and planets in arrangements. Nature explores throughout the galaxy. The speed of light is the universe's ultimate speed limit. In our everyday experience, we can always imagine going faster. A car moves at certain speed, but a plane goes faster, and a rocket faster still. It seems like there should be no absolute limit, that with enough energy, you could accelerate anything to any speed. But Einstein's special relativity revealed a profound truth. There is a cosmic speed limit built into the fabric of reality itself. And that limit is the speed of light in vacuum, approximately 300,000 kilometers per second. Nothing with mass can reach or exceed this speed, no matter how much energy you apply. As an object with mass accelerates closer to light speed, something strange happens. Its relativistic mass effectively increases, requiring ever more energy to accelerate it further. To actually reach light speed would require infinite energy, which is impossible. Only massless particles like photons can travel at exactly light speed. This cosmic speed limit has profound implications far beyond just motion. It means information cannot travel faster than light. Cause and effect are limited by light speed. There is no way to send a signal or influence faster than light can travel between 2 points. This structures the entire universe, creating cosmic horizons, regions of space that can never interact or communicate because the distance between them grows faster than light can travel across it. The speed limit makes time travel to the past appear impossible, preventing causality paradoxes. It ensures that simultaneity is relative. Events that appear simultaneous to one observer happen at different times for observers in different reference frames. The speed of light isn't just a number, a physical constant to be measured and recorded. It is a fundamental boundary woven into the structure of spacetime itself, a limit that governs how the universe operates on the most basic level. Black holes can evaporate over unimaginable timescales through quantum effects. For decades after black holes were first predicted by general relativity, they were thought to be truly eternal, cosmic traps that consumed everything and grew forever, permanent features of the universe that could never disappear. Then Stephen Hawking made a revolutionary discovery by combining quantum mechanics with general relativity. Near a black hole's event horizon, he realized virtual particle pairs constantly appear as quantum fluctuations. Normally, these pairs immediately annihilate each other, but near the event horizon, something extraordinary can happen. One particle falls into the black hole, while its partner escapes to infinity. From a distant observer's perspective, the black hole has emitted a particle, a phenomenon called Hawking radiation. This process slowly drains energy from the black hole, causing it to lose mass over time. The rate is incredibly slow for massive black holes, far slower than the rate at which they accrete mass from surrounding space. But in principle, if a black hole is isolated with no infalling matter, it will eventually evaporate completely. Smaller black holes evaporate faster than large ones. A black hole with the mass of the Sun would take 10 circumflex 67 years to evaporate, far longer than the current age of the universe. A supermassive black hole with 1 billion solar masses would take 10 circumflex 100 years. These timescales are so vast they defy human comprehension, longer than most other timescales in cosmology. But eventually, in the unimaginably distant future, when the last stars have burned out and the universe is cold and dark, even the most massive black holes will slowly evaporate away through Hawking radiation. In their final moments, as they shrink to microscopic sizes, they would evaporate rapidly in a final burst of radiation. Then they would be gone, disappeared completely, leaving behind only a puff of particles and radiation expanding into the void. The universe's darkest objects are not eternal after all. Even they are subject to quantum mechanics and thermodynamics, and given sufficient time, they too must fade away. We are made of matter that has been recycled through multiple stellar generations. The atoms in your body, the carbon and oxygen and iron and calcium, have ancient and complex histories. They weren't created during the Big Bang, which produced only hydrogen and helium and traces of lithium. Heavier elements had to be forged later in the cores of stars through nuclear fusion. But here is the remarkable part. Those elements have likely cycled through multiple stars over billions of years. When the first generation of massive stars formed from primordial hydrogen and helium, they fused lighter elements into heavier ones and then exploded as supernovas, scattering the newly created elements into space. Those enriched gas clouds became part of a second generation of stars, which fused elements further up the periodic table and also eventually died, some exploding and enriching the interstellar medium even more. This cycle repeated multiple times over billions of years. The iron in your blood might have been created in a massive star that exploded 7 billion years ago. That iron became part of a gas cloud that formed a second-generation star 5 billion years ago. That star might have eventually shed its outer layers as a planetary nebula, returning the iron to space. It drifted in the interstellar medium for hundreds of millions of years before becoming part of the molecular cloud that collapsed to form our solar system 4.6 billion years ago. From there, it was incorporated into the rocky material that formed Earth, later became part of a living organism, was recycled through the biosphere countless times, and finally became part of you. You are a collection of cosmic recycling, matter that has traveled across the galaxy, witnessed the birth and death of multiple stars, existed in various forms for billions of years, and now temporarily, for a brief moment in cosmic time, forms a conscious being capable of contemplating its own origins. The universe wastes nothing. It endlessly reuses, transforms, and recreates, building new structures from the ashes of old ones in an eternal cycle. Magnetars possess the strongest magnetic fields known to exist anywhere. Magnetars are a rare and extreme type of neutron star that possess magnetic fields of almost incomprehensible strength, trillions of times more powerful than Earth's magnetic field. Millions of times stronger than any magnetic field humans have ever created in laboratories. These fields are so intense they warp the quantum vacuum itself, literally changing the properties of empty space around them. Within about 1,000 kilometers of a magnetar, the magnetic field is strong enough to be lethal to any hypothetical human, not just because of direct magnetic effects, but because the field would disrupt the electromagnetic bonds that hold atoms and molecules together, tearing apart the very structure of matter. Your atoms would be stretched into elongated cigar shapes as the magnetic field distorts their electron clouds. Chemical bonds would break. The proteins and molecules that make up your body would come apart. Fortunately, magnetars are rare. Only a few dozen have been identified in our galaxy, and they're all safely distant from Earth. When magnetars release energy suddenly in events called starquakes, caused by stress in their ultra-dense crust suddenly fracturing and rearranging, they produce bursts of gamma rays so intense they can be detected from thousands of light-years away. One magnetar flare detected from 50,000 light-years away was bright enough to measurably affect Earth's ionosphere, despite traveling across half the galaxy. These objects represent nature pushing magnetic fields to their absolute physical limits, as strong as quantum electrodynamics allows them to be before even stranger physics would take over. Magnetars are cosmic extremes, demonstrations that the universe creates conditions far beyond anything we experience on Earth, regimes where our intuitions completely fail and physics becomes almost unrecognizably strange. The universe expands uniformly, carrying galaxies apart like dots on an inflating balloon. It is tempting to imagine galaxies as objects flying through space, propelled outward by the energy of the Big Bang like shrapnel from an explosion. But that is not accurate. Galaxies aren't moving through space in the usual sense. Space itself is expanding, stretching uniformly everywhere, increasing the distance between galaxies that are actually at rest relative to their local spacetime. No matter where you are in the universe, if you measure the motion of distant galaxies, you'll find them moving away from you. This isn't because you are at some privileged central position. It is because space is expanding uniformly everywhere. The farther away a galaxy is, the faster it recedes, not because it is moving faster through space, but because there is more expanding space between you and it. This uniform expansion is described by Hubble's law, which relates recession velocity to distance through the Hubble constant. It is a cosmic stretching, affecting everywhere equally, pulling clusters of galaxies apart from each other while the clusters themselves remain bound by gravity. Within galaxy clusters and within individual galaxies, gravity is strong enough to overcome the expansion, holding structures together. But on larger scales, expansion dominates and the universe continues growing. Its volume increasing, distances between separated objects increasing, the space between getting larger while the objects themselves don't expand. This will continue indefinitely. The universe will keep expanding, accelerating due to dark energy, growing larger and larger forever, eventually becoming so vast and diffuse that distant galaxies disappear beyond our cosmic horizon, unreachable and invisible, leaving isolated islands of gravitationally bound structures in an ever emptier apparent universe. Quasars are among the brightest and most distant objects we can observe. Quasars are incredibly luminous objects found at tremendous distances, often billions of light years away, making them among the most distant and energetic phenomena we can detect. Their name comes from quasi, stellar radio sources, because they initially appeared star-like invisible light while emitting strong radio waves. But they're not stars at all. They're the intensely bright central cores of extremely distant active galaxies, powered by supermassive black holes consuming vast amounts of matter. As gas, and sometimes entire stars spiral into the black hole, the material forms an accretion disk where friction heats it to millions of degrees. The disk glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays. Powerful magnetic fields channel some of the infalling material into jets that shoot outward at nearly light speed, extending thousands or millions of light years. A single quasar can outshine its entire host galaxy of hundreds of billions of stars. All that energy coming from a region smaller than our solar system. Some quasars are so luminous they're visible from distances exceeding 13 billion light years. Their light has traveled most of the age of the universe to reach us. When we observe distant quasars, we're seeing them as they existed when the universe was very young, less than a billion years after the Big Bang, when galaxies were still forming and the first generation of supermassive black holes were actively feeding. Quasars were more common in the early universe than they are now. As galaxies evolved and settled down, their central black holes ran out of easily accessible fuel. Most supermassive black holes today, including the one at the center of our Milky Way, are relatively quiet, not producing quasar-like emission. Quasars are cosmic beacons from the universe's youth, brilliant and violent, showing us what galaxies looked like billions of years ago, when the cosmos was young and wild. From a photon's perspective, time does not exist at all. This is one of the strangest consequences of special relativity. As objects approach light speed, time dilation becomes extreme. Time passes more slowly for fast-moving objects relative to stationary observers. As velocity approaches light speed, time slows towards zero. For a photon of light actually traveling at light speed, time dilation becomes infinite. From the photon's reference frame, if it had a conscious perspective, no time passes at all during its journey regardless of distance. A photon emitted from a star 10 billion light years away, traveling for 10 billion years from our perspective, experiences its entire journey instantaneously from its own frame of reference. It leaves the distant star and arrives at your eye in the same moment. Zero time elapsed. The concepts of duration, of waiting, of travel time simply don't apply. There is no passage of time. The photon exists in an eternal timeless now, connecting its emission and absorption events. Of course, photons aren't conscious and don't have perspectives, but the mathematics is clear. In the photon's reference frame, distances along its direction of motion are contracted to zero by relativistic length contraction, and time is dilated to zero. The journey that takes billions of years from our perspective takes no time at all from the photon's perspective. Every photon that has ever traveled through the universe, from the cosmic microwave background radiation released 13.8 billion years ago to the light from a candle, experiences no passage of time. We experience light's journey as taking time because we're in different reference frames, moving slowly compared to light. But the light itself knows no time at all, existing in a strange timeless state that connects distant parts of the universe in an eternal present moment. Eventually, the universe will become completely dark in the far future. The universe's future is written in the laws of thermodynamics and the continued expansion of space. Star formation has already peaked. We live in an era where galaxies are still bright and active, still forming new stars from available gas. But this won't last forever. Eventually, all the available hydrogen gas will be used up, locked into stars or stellar remnants, or dispersed too thinly by cosmic expansion to collapse and form new stars. In about 1 trillion years, 100 times the current age of the universe, the last generation of stars will begin forming from the final reserves of available gas. Those stars will eventually exhaust their fuel and die. The smallest red dwarf stars, which burn their fuel incredibly slowly and live for trillions of years, will be the last stars shining. When the last red dwarf finally burns out, perhaps 10 trillion years from now, the era of starlight will end. Galaxies will fade from brilliant spirals filled with young blue stars and glowing nebulae to dark collections of stellar remnants. White dwarfs slowly cooling toward absolute zero, neutron stars spinning in darkness, and black holes that have consumed whatever matter remained nearby. The universe will enter the so-called degenerate era, where the only significant objects are these stellar corpses and the planets that orbit them. Over even longer timescales, gravitational interactions will eventually eject most of these remnants from galaxies into intergalactic space. Protons themselves may decay over timescales of 10 circumflex 40 years or longer, causing even stable matter to eventually disintegrate. Finally, even black holes will evaporate through Hawking radiation over timescales of 10 circumflex 100 years. In the ultimate far future, the universe will consist of a thin soup of elementary particles, photons and perhaps exotic forms of matter, all separated by ever-increasing distances as expansion continues, growing colder and more diffuse, approaching but never reaching absolute zero, in a state of near-perfect darkness and stillness where almost nothing happens anymore. An ending not with a bang, but with an infinitely slow fade to black. There are clouds of organic molecules floating in interstellar space. Space isn't just empty vacuum between the stars. In vast molecular clouds, astronomers have detected an incredible variety of complex organic molecules, the building blocks of chemistry and potentially of life. These clouds contain simple molecules like water ice, carbon dioxide, ammonia, and methane. But they also contain more complex organic compounds, alcohols like ethanol and methanol, sugars like glycolaldehyde, amino acids, and even molecules with benzene rings. One famous molecular cloud near the center of our galaxy, called Sagittarius B2, contains a vast amount of ethyl formate, the chemical compound that gives raspberries their flavor and contributes to the smell of rum. If you could somehow survive in that cloud and had a way to smell without immediately dying, it would smell vaguely like raspberries and rum. There is also an enormous cloud of ethyl alcohol, ordinary drinking alcohol, containing enough to fill billions of bottles. These organic molecules form naturally in the cold conditions of interstellar space through chemical reactions on the surfaces of dust grains and through gas phase chemistry driven by ultraviolet radiation from nearby stars. The discoveries suggest that the chemical building blocks for life are common throughout the universe, formed naturally by cosmic processes, scattered through space waiting to be incorporated into new planetary systems, where they might eventually lead to the emergence of living organisms. The chemistry of life isn't special or rare. It is universal, occurring throughout the cosmos, wherever conditions allow. Every molecular cloud is a chemical laboratory producing organic molecules. Cosmic factories operating on scales of light years, churning out the precursors of biochemistry, long before planets form. White dwarf stars will eventually cool to become black dwarfs. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers in a planetary nebula, leaving behind its hot, dense core, a white dwarf roughly the size of Earth. But with mass comparable to the Sun, white dwarfs no longer generate energy through fusion. They simply radiate away their stored thermal energy, gradually cooling over billions of years. Eventually, after an incredibly long time, a white dwarf will cool to the point where it no longer emits visible light, becoming what is theoretically called a black dwarf, a cold, dark sphere of degenerate matter, essentially a cosmic ember that has gone out, supported against gravitational collapse only by quantum degeneracy pressure. Here is the remarkable thing. No black dwarfs exist yet anywhere in the universe. Not a single one. The universe isn't old enough. The cooling process takes so incredibly long that even the oldest white dwarfs, formed from the first generation of stars to die billions of years ago, are still radiating heat and emitting faint light. The universe is only 13.8 billion years old. Calculations suggest it takes trillions of years for a white dwarf to cool to truly dark temperatures. In the far future, quadrillions of years from now, the universe will be populated with countless black dwarfs, invisible remnants of dead stars drifting silently through the darkness. There'll be monuments to stars that once shone, now cold and forgotten, dark tombstones marking where suns used to burn. But that era is so far in the future that it is almost beyond contemplation. For now, every white dwarf we can detect still glows faintly, still holds heat from the stellar furnaces they once were, cooling gradually toward an ultimate darkness they won't reach for eons to come. Our Milky Way galaxy is on an inevitable collision course with Andromeda. Our galaxy and the Andromeda galaxy, located roughly 2.5 million light-years away, are approaching each other at a relative velocity of about 110 kilometers per second. Despite the vast distance between them, gravity draws them together inexorably. Current measurements and computer simulations predict they will begin to collide in approximately 4 to 5 billion years. When the merger happens, it will be a slow-motion collision, unfolding over hundreds of millions of years. The two galaxies will pass through each other initially, their individual stars rarely colliding because the distances between stars within galaxies are so enormous. But gravitational forces will dramatically reshape both galaxies, creating long tidal tails of stars, compressing gas clouds, and triggering bursts of intense star formation. The supermassive black holes at the centers of both galaxies, each millions of times the Sun's mass, will spiral toward each other, eventually merging in a tremendous release of gravitational wave energy. After multiple passes and hundreds of millions of years of gravitational interaction, the two separate spiral galaxies will merge into a single large elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda. By the time this happens, our Sun will be nearing the end of its life, entering its red giant phase, if Earth still exists and hasn't been engulfed by the expanding Sun. Any observers would witness a dramatic transformation of the night sky over millions of years. The fuzzy patch that is Andromeda would grow larger and larger, eventually dominating the sky. New stars would fill the heavens as the galaxies interpenetrate. It would be a spectacular cosmic show, a reminder that even galaxies are temporary structures, constantly evolving, merging, and transforming over cosmic time. Every second, somewhere in the universe, stars are being born and dying. The cosmos is not static. It is a dynamic, constantly evolving system where creation and destruction happen simultaneously across billions of galaxies. At this very moment, massive stars in distant galaxies are reaching the ends of their lives, their cores collapsing catastrophically and rebounding in supernova explosions that briefly outshine their entire host galaxies. Those explosions scatter newly forged elements across space and trigger shockwaves that compress nearby gas clouds. Meanwhile, in molecular clouds throughout the universe, those compressions and natural gravitational instabilities cause regions to collapse, heating up until nuclear fusion ignites and new stars are born. This cycle of stellar birth and death has been ongoing for over 13 billion years and will continue for trillions more. It is a cosmic heartbeat, a universal rhythm of creation and destruction that drives the chemical evolution of the universe. Each generation of stars enriches the interstellar medium with heavier elements. Those elements become part of the next generation of stars and their planets. We live in a dynamic universe, not a static one. Every moment, the cosmic census changes. Old stars fade and die. New stars ignite and begin their lives. The overall star formation rate in the universe has actually declined from its peak several billion years ago. But it continues even now, somewhere in the observable universe. A star is being born right now. Somewhere else, a massive star is dying in a supernova. The universe continuously writes and rewrites itself, an ongoing story told in fire and light, destruction and creation, death and rebirth in an endless cycle that transforms simple hydrogen into the complex chemistry that makes planets and life possible. There exists a massive cloud containing more water than all Earth's oceans combined. 12 billion light-years away, surrounding a quasar powered by a supermassive black hole, astronomers discovered the largest known reservoir of water in the universe. This enormous cloud of water vapor contains approximately 140 trillion times more water than all of Earth's oceans combined. Let that sink in for a moment. All the water in all the oceans on Earth, which covers 70% of our planet's surface, multiplied by 140 trillion. The water exists as vapor, spread across hundreds of light years in the region around the quasar where the supermassive black hole's radiation has heated the surrounding gas. The water molecules formed naturally through chemistry in the extreme conditions near the quasar. This discovery, while surprising in its scale, actually demonstrates something important. Water is common in the universe. We found water throughout the cosmos, in molecular clouds, in comets and asteroids, in the atmospheres of planets, on moons, in the rings of Saturn, even in the tenuous exospheres of Mercury. Water molecules form readily wherever hydrogen and oxygen exist in appropriate conditions. The building blocks of life as we know it, particularly liquid water, are scattered everywhere in the universe, woven into the fabric of cosmic chemistry, present from the earliest eras of galaxy formation to the present day. The Andromeda Galaxy is visible to the naked eye from Earth, on a clear, truly dark night far from city lights, away from light pollution. If you look up at the constellation Andromeda, you can see a faint smudge of light, barely distinguishable from the background darkness. That is the Andromeda Galaxy. M31, the nearest large spiral galaxy to our own Milky Way. The light you see has traveled for about 2.5 million years to reach your eyes. You are seeing Andromeda, not as it exists now, but as it was when that light left. 2.5 million years ago, long before modern humans existed, back when our ancestors were primitive hominids just beginning to use stone tools in Africa. Andromeda contains roughly 1 trillion stars, more than our Milky Way's estimated few hundred billion. Those trillion suns orbit a supermassive black hole at the galaxy's center. Andromeda has at least 14 satellite dwarf galaxies orbiting it. It is larger than the Milky Way in terms of stellar mass and diameter, spanning roughly 220,000 light-years across. When you look at it, you are witnessing the majesty of another island universe, across the void, a cosmic neighbor containing hundreds of billions of worlds, perhaps countless planets, possibly even life and civilizations looking back across the gap between galaxies, wondering if they're alone. It is a humbling and awe-inspiring sight, a reminder that we are part of something far grander than ourselves. Inhabitants of one galaxy among billions, looking across millions of light years to see another. And so, dear traveler, our gentle journey through the cosmos draws quietly to its close. We've drifted together through the universe's greatest mysteries, from the quantum foam seething at reality's smallest scales to the grand cosmic structures spanning billions of light years. From the birth of time itself to the heat-death waiting in the incomprehensible future. From the silence of space to the ringing of gravitational waves, we've touched infinity and contemplated nothingness. We've seen that you are made of stars, that time is flexible, that space expands, and that the universe is stranger and more beautiful than any story ever told. If your eyes are growing heavy now, if your thoughts are beginning to drift like dust motes in a sunbeam, if you feel yourself floating gently in the darkness, that is exactly right. Let the vastness cradle you. Let the mysteries wrap around you like a blanket woven from starlight. Let yourself sink softly into sleep, held by the same forces that hold galaxies in their orbits and guide photons across the void. The universe has been here for 13.8 billion years. It will be here for trillions more. The stars will keep burning. The galaxies will keep turning. Space will keep expanding. And the cosmic story will continue. whether you are awake to witness it or not. For now, you've traveled far enough. You've seen wonders beyond counting. You've touched the infinite and glimpsed the eternal. Now it is time to rest beneath the quiet gaze of distant suns, to drift in the cosmic current, to let your consciousness dissolve like morning mist into the vastness that surrounds us always. Thank you for wandering with me through these celestial gardens, for lending me your attention and your wonder. May your dreams be filled with nebulae and newborn stars, with galaxies colliding in slow motion and black holes singing their gravitational songs. May you sleep deeply and peacefully, cradled by the universe itself. Good night, fellow stardust. Good night, temporary arrangement of cosmic atoms. Good night, consciousness briefly emerged from the void and destined to return. The universe holds you gently. Rest now, all is well. The story continues, but for tonight, your chapter can pause. Sleep well, dream softly, and know that you are home in the cosmos. The stars are watching, the universe is singing, and everything, always, is exactly as it should be. Rest now.